Day. We're not in school next Thursday for report card pickup. So then we'll have Friday review day and Monday test. So talk to your physics people. I call next Monday. You guys keep on getting the test on the same day, yes? Yes? Alright. Who remembers Small World, the unit Small World from Math 3? I do, Mr. Remus. Who said that?
Everyone.
Okay. The 2 to the x function, you put it an x value of 0, what do you get? 1. You put an x value of 1 in, what do you get? 2. You put an x value of 2 in. 4. You put an x value of 3 in. 3. Do you guys remember this?
No.
Okay. If I wanted to know the long way how to calculate the change in y over change in x, which is what you guys did, at this point, the long way, what would you do? How did we start out doing this stuff? I want to know what the rate of change is approximated at this x value. Subtract what? You're looking at how to prove it. You're doing math 4. You're getting fancy. That's how you prove the divided difference and all that stuff. That's how to prove it's an exponential function. What I want to know is, how did we, in the beginning of the year, start out finding the change in y over change in x at a specific point? How do we approximate it? Yeah, plus h. And I'm just going to do a value here, okay? So let's say at the point 0, 1. What's a point really close to this? Well, I'm going to call the point 0, 0, 1. And then what's the y value? Be careful. What's the y value for this x value? For that function? Or 2 to the point 0, 0, 1? Because you put x in input. X there. So you put the x in. And then you get an output. Does that make sense, guys? So what is this value? What is 2 raised to the point 0, 0, 1 on your calculator? Give me like 5 or 6. Give me a whole bunch of decimals. 6, 9, 3, 3. 8, 7. That looks good.
There's 3 zeros.
There we go. Okay? And if I wanted to know the change in y over change in x, I'd go old school on here. Change in y over change in x would be this number minus 1 over this y2 minus y1. And what is that change in y over change in x? Off your calculator. We're writing this in your notes together. We're doing all this stuff. We're calculating. We're taking notes. We got it all going. You guys are efficient calculating machines. What did you get? 0.6933. Okay, cool. That looks good. Okay, let's just see how close we are on our calculator. So what's the calculator telling me the derivative is at 0 for the 2 to the x function using the graph, let's say. And how do you do that? Great question. For the group, I want you to calculate the dy dx at 0 of the 2 to the x function. How do you do that? Well, you need a calculator 1, you need a graph 2, and then what do you need? What do you need to hit? Second calculate 7, which is dy over dx. And what do we get? 0.693. 14. Okay. Well, that's pretty accurate. You guys, you see we just did this? When we had it accurate to 3 decimal places, not bad. You know what I'm saying? Let's do one more point old school way. The point 1, 2. At the point 1, 2, we have the point 1, 2, and then we have the point really close to it, 1.001, comma.
2 to the...
Yeah, 2 raised to that, which is what? 2.00138.
6775.
6, 7, 7. Cool. All right, let's change the Y and change old school. We're kicking it old school. I'm going to get my parachute pants, my Z calves. We're going old school on this. You making fun of my Z calves? I still think I still have them. I don't understand what's so funny. Minus y2 minus y1 over x2 minus x1. Now what do you get? Since we're calculating it all together, we're not just going to stare at me, because that would just make me nervous. Okay, great. What do we get?
1.386. 77.
Okay.
No, wait.
What is, let's calculate dy dx at 1, and what do you get? Yeah.
1.38629.
Okay, cool. And now just do for 2 and 3, just use your graph. Because it looks like we're right on it. We're doing really good by hand. Let's do second calculate dy dx at 2 and 3. And let me know these numbers.
At 2 it's 2.77.
Give me a couple more decimals.
259.
Okay, what about at 3?
5 point. Okay, 5.545177.
5.54.
517.
This is 5 at 3?
Yeah.
Yeah.
5.5.
451779.
Okay. So, here's the deal. This is the derivative of 2 to the x at specific points. What's the rule? Well, look at there, like, how do these numbers compare? So 0.69314, and then this number, and then this number, and then this number. How do they compare? So we're throwing some ideas out there. You guys talk about it. How do these numbers compare? How does this number compare to this number? What is it? This one's double?
Yeah, they're all doubles.
And then this one's double this one? Well, how can we do this? How can we compare this one, and this one to this number? Starting with this number, we double this.
It's times 2 times 4 times.
And this one is times 4. And this one is.
Times 3.
So you're saying it's this number for this one times 1. And this one's this number times 2. And this one's that original number times 4. And this one's that original number times 8.
Gosh.
Does anyone notice any patterns, like, overall?
It's the same.
It's this number to get the derivative at a specific x value for this function. The derivative is equal to this weird number times 2 to the x. You plug in an x value of 0, you get 1. You plug in and that's times 1. You plug in an x value of 1, you multiply this thing by 2. You plug in an x value of 2, you quadruple this number to get this. You plug in a 3 in for x, you multiply this number by 8, and you'll get that. Does that make sense, you guys? That's the rule for this exponential function. The only problem is what the heck is that number? And this is how we left it at Small World. We did this one, and we did one more, but we left it here. This is the rule, but is it always 0.69314 for every function? And where the heck does this number come from?